let's review the flowchart again. So we always start off by looking to see if we have a recognizable form. So either a geometric series or a p-series. If we don't have one of those, our next step is to try the divergence test. If the divergence test is inconclusive, then we have two choices here. So we need to look at our series and decide, are all the terms positive, or do we have alternating terms, meaning they go positive, negative, positive, negative. We're going to start by looking at the test for positive terms. We have three tests: the integral test, the direct comparison test, and the limit comparison test. We'll start with the integral test. The key for the integral test is if you look at the series and it looks like something you could find the antiderivative of, maybe it's a simple u sub or something like that, then you would want to use the integral test for that. So let's take a look at what the criteria and the rules are for using this test. So the first thing we want to do is rewrite our series so we have it as a function of x. And once we've done that, we're going to graph it and we're going to take a look to see that it is continuous, positive, and decreasing. Okay, so it must meet all three of those criteria or we can't use this test. Okay, and the way that I remember this is one of my favorite TV shows is the Chicago series Fire Med, but Chicago PD, so CPD, continuous, positive, decreasing. Right, once you've checked to make sure that you've met that criteria, then you're going to take the series and rewrite it as an improper integral and evaluate it. So if your f of x is continuous, positive, decreasing, and this integral from k to infinity of f of x dx converges, then your series is also going to converge by the integral test. And similarly, as long as f of x is continuous, positive, decreasing, this integral from k to infinity of f of x dx diverges, then your series is also going to diverge by it. All right, so let's take a look at a problem. So this is number 8. I have the series from n equals 1 to infinity of 1 over n. Okay, so I want to check to see if it is continuous, positive, and decreasing. Okay, so to check that it's continuous, positive, and decreasing, I'm going to put this into my calculator. So I have 1 over x, and I'm going to take a look at the graph. Now remember that a series starts either with n equals 0 or some sort of positive number. So the only part that I'm interested in is the part that matches where my lower bound is. And then going out, obviously, into infinity. So I look at this picture, and this is definitely a continuous function from 1 to infinity. So that works. All the terms are above the x-axis, so it's positive. And then the function is decreasing. So I meet my criteria. That means my next step is to go ahead and write the improper integral from 1 to infinity of 1 over x dx. So make sure you're doing all of this in x. You cannot do this in n. Integrals only work for continuous functions, which is why we're using this x. So you need to rewrite this with the limit as r goes to infinity. The integral from 1 to r of 1 over x dx. So this is what we did in section 7.6. So this is hopefully a little bit of a review. And then I have this is equal to the limit as r goes to infinity. The antiderivative here is ln of x, evaluated from 1 to r. So I'll plug that in. I have the limit as r goes to infinity of ln of r minus ln of 1. As r goes to infinity, ln of r is going to go also to infinity, which means this integral diverges. And now I'm ready to do my write-up. So my write-up is going to be, since f of x equal to 1 over x is continuous, I'll just write CONT, positive POS, and decreasing DCR, and the integral from 1 to infinity of 1 over x dx diverges, then, or therefore, whichever you'd like to use, the sum from n equals 1 to infinity of 1 over n diverges by IT. So you want to make sure that you state which test you're using to make that conclusion. Okay, so there's your write-up. And I want to say a few more things about this. This series actually has a name. It's one of the few that has a name. It's called the Harmonic Series. And it is, if I was listing these terms out, this is 1 plus a half plus a third plus a fourth plus a fifth and so on. We looked at this one a little bit ago when we did the divergence test, and you'll remember that that limit was 0. So this is a case where if the limit is 0, the series diverges. And then I have one other thought on this. This is actually a p series. So this is 1 over n to the first. So that power is a 1. So p would be equal to 1 here. And that would mean that that diverges by the p series. So sometimes there's multiple different tests that you can use on a series to determine if it converges or diverges. Sometimes there's really only one good test to use.